Hello, we are team on Semiconductor. Our project is Power Output Driver Automated System for Integrated Circuits Over Time. Obviously, that's quite the mouthful, so we just go by POTUS. My name is Nicholas Amore. I'm an electrical engineer. With me today is Alex Cressman, computer engineer, Robert Robinson, electrical engineer, and Luke Doden, computer engineer. On Semiconductor is an international company with a location in East Greenwich, Rhode Island. They're a leading supplier of semiconductor solutions with a focus in automotive applications. They develop important parts such as switching regulators, smart FETs, and relay drivers. Of particular interest to us on this project are the relay drivers. These parts are exposed to a wide variety of inductive loads throughout their lifetime. So it's imperative to get customers important data such as maximum current and maximum energy so they know the survivability of the part. The current system on employees is seen here. At the top left, we can see that they have to first set up the board, then they must send a pulse to the IC, capture the oscilloscope data from the test, then increase the pulse. This is repeated until the output actually does fail. With these ICs, there's anywhere from 4 to 12 outputs, so this test must be repeated continuously until the part is fully tested. Once the part is fully tested, the test is complete, and they must reset up the board for the next part. We had done this test setup on our first day at ON, and it took us to test like 3 parts about 5 hours. So this is an extremely tedious process, and there's a high potential for user error. So what are we going to get out of doing this project? For one, we're going to reduce the time that it takes the employees to do their test. We're going to significantly reduce the time for IC testing, down from hours to minutes. With that freed up time, the employee can run additional tests on the chip, and then that will allow them to provide additional data to customers so they can better tailor the part to their needs. Lastly, there will be a significantly less potential for user error. So the anticipated best outcome is to take the current system and fully automate it. Some key features to that is an automated data extraction, so taking data from the oscilloscope and presenting it in a usable fashion, such as through Excel or an onboard display. Arduino-controlled PWM, so removing a clunky function generator that needs to be continuously updated. And then lastly, creating a supporting PCB for the aforementioned features. This is a block diagram of the anticipated best outcome. The electrical side is focused on designing the Capstone test board, which has key features such as the microcontroller, the safety shutoff, switching topology, and OLED displays. The computer side is focused with the data extraction from the oscilloscope, as mentioned, in addition to making a user-friendly interface to put important test parameters onto the test board. Now Robert Robertson will discuss hardware specifications.
A critical component for the success of our design is the automation of the selection between outputs one at a time. This will allow us to run the testing fixture with minimal human interaction. In order to accomplish this, we need to implement something called a switching topology. After several iterations, we decided to base our design around a relay. As you can see on screen right now, the relay is just this large rectangular block. At rest, the relay is open, which corresponds to an inactive output. Once the relay is excited by a 5-volt regulator, as seen right here, the relay closes, which corresponds to an active output. In order to prevent the premature activations of these outputs, however, we need to introduce an NMOS, seen right here, which disrupts the connection between 5 volts and ground. Once that NMOS receives a pulse from the mega, the NMOS activates, which completes the connection between 5 volts and ground. A consequence of the nature of our project is often when we're testing these parts, they tend to fail in a short condition, and as we have a power supply attached directly towards the path of that short, large amounts of current may be introduced to the system, potentially damaging it if left unabated. So in order to alleviate ourselves of this problem, we implemented a relay switch. The basic idea of the safety switch is to disrupt the connection between the inductor and the circuit using a FET, creating an open. Specifically, we have an NMOS cascaded with a PMOS. Once the mega sends a signal to the FETs, the battery voltage is attached to the inductor. Once the pulse ends, the pulse shuts everything off, detaching the battery voltage from the inductor, wherein the inductor now flows safely through the system. In addition to these schematic accomplishments, we've also completed our PCB design. So we decided to go with a 4-layer board for our own simplicity. This allows us to run the inner layers for power and ground, and the outer layers host our physical components of the board, as well as our routing traces. The layout of the board is shown on the screen right now, with the Arduino Mega being rested at the center. To the left of that, our output switching topology repeated 12 times for 12 outputs. To the top, we have our power as well as safety switch, and to the right, we have our OLED displays. With our hardware specifications out of the way, I would like to segue into Alex Cressman, who will discuss the software implications of our project.
One of our key accomplishments was the Arduino-controlled pulse width modulation. This was used instead of a signal generator. A signal generator, as shown in this photograph right here, proved to be rather slow and tedious because of its setup time, and you can only send one pulse width at a time. Now with our PWM, not only are you able to send one pulse width at a time, but an entire pulse wave with varying pulse width. Shown in this GIF right here, it starts at the initial and increments all the way up to the maximum. Also duly note that we use an Arduino Mega because of its many I/O pins. To control the Arduino, we created a GUI to go along with it, shown in this photograph right here. The user is allowed to input the initial pulse wave, the maximum pulse wave, and the incrementing pulse waves in between the initial and maximum. All this data is then showed on the programming screen right here. Once the user clicks the start button, located right there, all this data is then forwarded over from the PC over to the microcontroller, and using one of its many I/O pins, it sends the pulse wave that the user created. Also to note that the GUI comes equipped with a test results screen that shows the maximum energy, maximum current at that current pulse width, and all this data is taken directly from the oscilloscope. This data can also be found on the board with the dual LED displays. As shown again right here, we have testing results with the energy, current at that current pulse width taken from the oscilloscope, and it shows the pulse wave that the user created under the programming OLED screen. I'll give it off to Luke to talk about data extraction.
The system uses a Teledyne LaCroix oscilloscope to capture voltage, current, energy, and our pulse. For our purposes, we're concerned with current and energy. We like to extract this data, and we do so using Visual Basic for applications within Excel. Teledyne created a software utility tool called ActiveDSO, which allows us to communicate and control the oscilloscope from within Visual Basic. So how it works is the program sweeps cursors across the current waveform and the energy waveform, reading this data and outputting it to various Excel spreadsheets and graphing them as seen here. We also read the peak energy and peak current values and output those to the OLED displays as well as the GUI displays. Some remaining challenges we have for next semester include gathering data on the IC temperature along with energy and current. And we like to do a full system evaluation on multiple different ICs. We like to test the system using multiple driver configurations. And we like to create the system independent of a PC. As you see here, this is our block diagram for this semester with the PC included. Next semester, our block diagram will look something like this, where we don't have the PC anymore. We just have the microcontroller acting as a PC. Previously, we had the GUI. We had the user use the GUI to input the pulse wave and then send the pulse. Instead, we're going to use onboard push buttons, and this will allow for simplified testing, and the system will take up less space on the workbench. Finally, we like to do full documentation of all of our findings. And with that, I'd like to thank everyone that helped us with our project. Thank you.